Welcome everyone. In this video I'm going to talk about my miniature tensile testing machine a little bit. So I will guide you through all the parts and all the electronics and everything. Not in too much details, but still I will share as much as possible. So I would like to talk about the motivation behind this machine. So I'm using different tensile testing machines during my work, and I use a very special tensile testing machine which can be used inside a chamber of a scanning electron microscope, and I was doing a lot of work with that, but I was not satisfied with the software of that machine and also with the capabilities of that machine. So I thought that I can do it better. So roughly 1.5 years ago, I started to work on this project by starting to plan and design everything and buying the parts piece by piece from the internet, from different sources. And yeah, so I came up with this prototype or iteration, however you call it. I made this wall machine that you can see on the picture, and I also made the electronics, and I also wrote the software, both for the controlling system and also for the, let's call it, data processing system. And I will show you everything, how it works. So this is the story of this machine in a nutshell. And now let's start with the one of the most important part of this machine. So I will show it. It's this motor here on the right side of the picture. This is a NEMA 23 stepper motor, and there is a planetary gear with 15:1 gear ratio. So I use this motor because I can provide high enough torque with reasonable speed, because there are a lot of gears in this machine. So I need something which can provide high speed and high torque. So at the end, where I have the crossheads, I will have reasonable speed. Previously I was using a smaller motor. I try to show it. This guy here. You can see the ID of it. So this is a NEMA 17, so one smaller by one level, or I don't know how they group these numbers, but this is smaller than the previous, and this has higher gear ratio, but you sacrifice a lot of speed. It's still okay for these types of tests, but I wanted to be able to move the crossheads here rather quickly. So yeah, we have the motor here, and then here there are different pulleys and timing belts, but this is not the final part, because previously I managed to break these belts, because this is like 6mm wide, so it's very weak. But now I have these are 9mm, more thicker, and also the pulley wheels are wider, so we have larger surface, and I will use this in the future. So the power is transmitted by pulleys here from the planetary gear, and then from this pulley wheel here, as you can see, we have a shaft, and then this shaft has two worm gears just here. So it's like this guy, and then it is connected to a worm wheel like this. So this is some sort of steel, I think C45, and this is brass, as you can see from the color. So they mesh together in this kind of orientation or geometry. So you can see. So this shaft transfers the power to the two lead screws here. So here there is the pulleys have 1-to-1 gear ratio, so nothing is transformed here regarding the torque and the speed. And then here where we have this system, like here, this is a 20-to-1 gear ratio, so we lose a lot of speed, but still we have a lot of torque. And this is very good because you can transform the torque or the speed in a very small volume, let's say. So I mean, this takes up so small space, but this is not so efficient, so there is a lot of friction, and you have to make sure that you align these parts perfectly. And then this shaft here is supported by two support bearings, so they can take the axial forces. And that's very important, because if you move these gears and these gears like meshing into each other, there will be always an axial force, and then you have to be able to hold against that force. So this is one part of the support, and then we have the two lead screws. So this is a special type of lead screw. I show you. I use this. I don't know if it's in focus, but you can see that from the middle, one thread is right-handed and one thread is left-handed. So if you rotate the nuts in the same direction, either they go towards each other or they separate. Why this is important? So I was thinking that if I just use a simple screw, a lead screw with a single thread, then I will have to use something at one end of this support system or bearing system. So if I have this crosshead, I have the sample and the load cell and everything. The load cell has to be fixed to a very rigid point, and also the bearings should be very strong, because basically they will experience similar forces as the specimen in the middle experiences. So I wanted to get rid of this problem, and I did not want to struggle with these bearings. So I thought that if we have a twin lead screw, so like this or this, you can see, then we can sort of confine the force between the two crossheads, and then we don't have to worry about the support bearings. Still, I have very strong bearings here, so they can take, I think, like 2 tons equivalent of force, or even more per piece, but I will replace them. I will show you a new design later. So we have these two lead screws, and the advantage of this type of lead screw is that you can confine, or you can restrict the most of the forces can be restricted in between these two crossheads. And then here I did not want to remove this, but I have a special grip which can hold the specimen like this. So the grip is like an L-shaped piece of metal, a bulk metal, and then there are like 2 pins on the side. So the 2 pins go into the side of the specimen, and then in the middle there is another type of screw. I just use it to push this small rectangular shaped part to keep this flat, but the middle screw does not take any load. It is only just to push down the sample, so it will lie on the specimen holder perfectly. So this is the specimen what I have here. The parallel length here is like 5 millimeters. So that's the part which deforms in the optimum case, and then we fix it by the grips here, so you can see. So we have this, and then you can see that the cable is coming out from this cylindrical shaped something. That's the load cell. This load cell can take or can measure up to 500 kilograms or 5 kilonewton. So this is all basically. So we measure the force here, and then here I tortured a caliper, a digital caliper, and I transformed it into digital, yeah, it's sort of a displacement sensor. So I printed some sort of consoles here, which are basically connected to these brass nuts, but on this side obviously. And then you can see I drilled 2 holes on the grips, and then I screwed it to this. So I don't measure the very exact displacement, because if you really want to be scientifically accurate, then you should measure the displacement between the parallel lengths of the specimen. But the space is just so small, and of course I don't have the best tools and everything, that I just measure the displacement of the 2 crossheads, and that's not so precise at all, but it's something at least. But we can use a camera and put some speckles or something on the surface, and then we can have a digital image correlation, and that's very good for displacement measurement. And you can use the digital microscopes or whatever, which you can buy very cheap, and you can use that. And then we have this simple bearings, like crazy cheap bearings, KP something, depending on the diameter of this hole. They have different numbers. This is, I think, KP10, because it's 10 millimeter in diameter. And then that's all. And I have this huge construction steel board. I designed all the holes and everything, and I found a company which can cut everything out by laser. So this piece is cut out with laser. And then there are some other parts, because of the distances between the different bearings and the heights. I had to make sure that everything is connected properly. So I used some nuts, washers, or pieces of aluminum blocks to make everything in level. So this is all regarding the mechanical part. So I show you the electronics in a second. So the electronics consists of 2 main parts. I already made some changes, so this is a huge mess, but it's just a part of an iteration. So firstly, we have this TB6600, or however you pronounce the name of this. So we have this controller for the motor. This is a huge overkill. We don't need this much current and this much complexity that this can provide, but I wanted to remove the controller from this box because I have some problems with noise, and my first guess was the controller of the motor, but it was not the best guess, I think. I will tell you later. So we have this main controller. So it is connected to some sort of power supply, and then it is connected to the motor, obviously. So I made some fancy connectors here. And then it's connected to an Arduino. It's connected to an Arduino Nano, which is connected to another Arduino, it's a Uno. And then within this box we also have a level shifter. That's because of the digital caliper, because the digital caliper operates at roughly 1.5 volts. But in order to be able to read the signals, its output is some series of square waves. So in order to be able to see those square waves with the Arduino, we need to shift the level to the logical level to 5 volts, so we can have this. We can see the signal and process it. So this is happening here, and there is also DC-DC converter in order to convert down the 5 volts from the Arduino to 1.5 for the caliper. And then we process the signal of the load cell, which is an HX711 circuit. It's very simple. You can buy it for any kind of weight gauges or whatever. So it's a 24-bit AD converter basically. And then this is connected to the main Arduino, which is the Uno. And then it's connected to the load cell with this orange cable. So why, you can ask, why do I have 2 Arduinos? So the main Arduino here, this communicates with basically 3 things, or 4. One is the computer, and another is the load cell. Another is the caliper, and then with another Arduino, which only and just only controls the motor. Why? Because there are so many things to do here. So send the data to the computer, read the data from 2 different sources, and control the motor meanwhile, that the speed of this Arduino is not sufficient. I tried this non-interrupting programming and everything, but I was not able to squeeze in the controlling of the motor into the process of the other things. So if you are trying to use high speeds for the motor, so you want to make a very dense square waves, let's say, then the motor will not be able to move smoothly and continuously. So I say that I send a command from the computer to the main board, and the main board tells the controller that, okay, let's move whatever number of steps with this kind of rate, and that's all. And I can start it, interrupt it, whatever. And then, since this Arduino, the small one, the Nano, only takes care of the motor, then there are no interruptions, the motor runs smoothly, and everything is very nice. But if I run everything, then I still have some problem with the caliper, because somewhere here, maybe because of the alignment of the cables or whatever, I still have to work this out. There is some noise or something. So if I try to read the values from the caliper, I cannot read it because the numbers are jumping between very unrealistic values. So somewhere in this circuit, the caliper picks up the noise, and therefore I cannot use it properly. So this is one of the challenges I have to solve. And I show you some other parts because I already have the next iteration of this machine planned, but I just did not have any time in the past several months to do any work on this. But I show you what am I thinking about. So first I show you some other parts. So this part is the crosshead, this guy here. So 3 of this is put together, and then a nut or a bolt is going through this part. You can see the end of the bolt, and also the bolt for the load cell. And then this is like centered. This is also cut by laser. It's the same material as the base plate. So this is here. And then I also have another plan with the driving. So this is a small DC motor. You can see the details here, I hope. And then planetary gear. And then also this has an optical decoder, so I can see the speed and also calculate the distance. So this would be also nice, but I have some problems with other things in this machine, so I want to solve them first. Then, yeah, I already showed you, but this is basically the support bearing. So then here you can see the inside, the bore and everything. And there are several types of this. So this is the one that you mount on surfaces. but there are also other types which can be put in holes like this. So this is without the body, but basically the same guy. And then I show you something nice which is related to this soon. But this is better because then you can design some other holder instead of these big chunky things, and you can miniaturize this more. In fact, this is like twice as bigger as my final plan, but yeah, since I'm limited with a lot of tools and money, I go slowly and I cannot do everything at the same time. But for example, you can see that this part is very large, so it takes up like more than 1/3, almost half of the board here, or plate. Then I thought that, okay, we can save some length by keeping almost the same width, but putting the motor parallel with the lead screws. So sort of like this. So putting it here. So we save like 5 to 8 centimeters on that side, and then we can do something on this side, and that's not a problem. Length is more problem. Also, I will cut this down to shorter things because, yeah, just physics, or the physics of these materials. Steel or any metals in general, they don't have good elongation, right? So let's say if you have some very fancy thing, then 100%. So the displacement of these individual pieces, if you have a similar specimen, so this is 5 millimeter and everything gets elongated as it should, then 100% elongation is 5 millimeter again. So these parts individually will move 2.5 millimeters, right? So therefore I don't need like I don't know, 5 centimeters on this side. Maybe I need 1 and 1 centimeter. So I say that, okay, you can print polymers, so you can test those with the similar geometry. You can put in paper, you can put in rubber or whatever, so maybe you will need a longer like range of motion, but still you don't need 5 centimeter on both sides in this direction, because that is like 10 centimeter total elongation. So we can squeeze this down, and also this part can be redesigned. So now I show you what I'm working on right now. So I designed a new holder and printed it at home. I have a 3D printer, so I could play around with prototyping. But you can see that I showed you some other type of bearing, like this guy here. And then I made a design which can accommodate these bearings, but of course I messed up something, so, and the printing was not perfect, so I cannot fit it, but this should fit here. But the final plan is to have these kind of things. So I have these nice bearings, and they should go in these holes right here and here. And also these bearings, which are now facing inside, or which are placed inside, then they should be in this hole. So there should not be any protruding parts. So you see that I have the lead screw, I have the shaft and the worm gears here, which are now here. And I also have the bearings, which are support bearings, so they can take the axial force. And then these bearings should go in this kind of part here, this place. And then now I just want to make the alignment. So we have the bearings inside, and then these guys go in, and they are like perfectly meshing together when, yeah. And then I will have some place here on the side of this part where I can attach the motor. So this will come parallel like this, and either I will do with the worm gears again. So probably I put the worm gear on this motor, and then I put the worm wheel on this shaft here, and then I drive it like this. Or we have these conical shaped gears, right? Bevel gear, I believe. And then I just need two of these. I have it, but I just put one on the table. So yeah, one comes here, whatever. So one comes here on the shaft. I hope you can see it. And then another will be on the end of the motor. And then this is 1:1 ratio, so I don't lose any speed or the torque. And then it's done. Only thing that I have to make sure that everything is nicely aligned, and therefore no problems with torque. Even if I don't care about the height of this, let's say, alignment, I can make this a bit taller, and then have this as a single piece of block on the top, and then I can put the motor on the top of this wall stuff here, like this, and then use some bats again, like this. But I don't like that idea, so I want to put the motor next to the shaft and parallel with the lead screws. And then I show you that if I use this kind of arrangement, then yeah, so this whole thing is becoming a bit shorter. Of course these are not included because these are in this part, but now since the print is running a bit shorter, or how to say, so this part is a bit more narrow than I originally planned due to the printing and my poor design. So I cannot fit this into the hole right now, but that doesn't matter. So yeah, this will be like shorter by 1 centimeter at least than the original alignment, and a bit less wide, if you see. So now yeah, you cannot see, but please believe it. So this part is now aligned with these two guys are parallel, but then you see that we save some space there. So I have this as my next idea. So now I have to solve like basically two serious issues. One is the noise, which is interfering with my caliper, and the other is this new type of support for the bearings and the drive. So yeah, this is all that I can show you right now, and I think I will also show some short clips about the software. So yeah, see you there. So this is the software that I use to capture the data and process the data. Now I haven't connected to the Tensile tester, so I just show the user interface of this thing, and you can find more detailed discussion about this software in my other videos. So basically we can select the Arduino, it will show up on this list, and you can select the port, which is the Arduino's port. You connect to it, and then you can set up everything for the testing. So you can set up how much distance you want to move. This is useful if you have different specimen, or you want to move back to the original or default position after you finished with the test. Then for the testing you can set up the file name, and you can save the file into a simple txt file. You can set up the crosshead speed. This will be calculated based on the gears and everything, and the stepper motor's speed. So you will see it here. And then you can choose that what kind of value you want to use for your test. So for example, if you just want to interrupt the test at 10% elongation, then you select that, you write in the number, and then you hit go, and then the software will do everything. We also have to define the details of the specimen, such as the gauge length and the cross-section area. And therefore, after we have these two values, then we can have the engineering strain and stress and true strain and stress based on these values. They are needed because by default we just have the displacement and force, but from that we have to calculate the strain and stress values. And then in this window, in the white area, we will see the graph or chart which will be drawn during the test. And then yeah, we see some position and the time of the measurement. So this is just a very simple software. It does what it has to do, nothing extra and nothing more. But yeah, it's good enough. And then if you want to see how this works, then I have other videos where you can see this program in action. So I hope this was useful and you learned something, and if you have any comments, suggestions, just let me know please. So see you.